So welcome everyone. Thanks for joining us, for coming. Today is World Quantum Day, the 14th of April, and to celebrate this day, I'm going to give you a friendly introduction to quantum games. But first, let me say what the World Quantum Day is. You can check in that web page over there. If you just click, then you can find the events that are all over the place. And there's something in Cork related to quantum optics or something like that, and that dot is us, okay, the second one. And the main aim of this day is to promote the quantumness or the awareness of the quantum world. And you might be wondering why 14th of April. For me, it's very weird as well. Well, 14th of April is the 4th of 14 and is related to the Planck's constant. Usually, maybe you know the Planck's constant to have this value, 6.73 in joules per second. But when you write it in electron volts, then it's almost 4 times 14. Okay, so that's why the 14th of April. If you write the Planck constant, the reduced Planck's constant, you could get another date. But anyway, I don't know why it was picked to be this day. Okay, so who am I? I'm Victoria Sanchez Munoz. I am a PhD student in the School of Math at the UAG, and my supervisor is Michael McEdrick. Maybe you know him. And I am also the main coordinator and founder member of QIreland. Here you can check the webpage, the email. We have a Discord channel, a Twitter, and a Facebook, if you are interested. Okay, so yeah, now let's get into that. Let's get to introduce you to quantum games and what is that. So my goal with this presentation is to answer this question that maybe some of you have, which is what on earth is a quantum game, right? And to do that, I will try to introduce an example that it involves some robbers. But first, this is about games, so 2 lines about game theory. Game theory is just any interaction between players that want to achieve some goal. When you think of a game, you might think of chess, rock, paper, scissors, any games that you play for fun. But this has also an application in the real world. Not that it's not real, but it's useful to model the human behavior. So it's game theory is used in trading, for markets, in politics, in diplomacy, and biology, and so on. This is the definition of a game. And when you think of games, there are not only one way to solve a game, like what is the solution of the game? Especially when you work with human behavior and markets and everything, what is the solution actually? And one very popular solution concept, we call that solution concept, is Nash equilibrium. In a Nash equilibrium configuration, no player wants to unilaterally deviate from that configuration. Okay. There's this wonderful film called A Beautiful Mind. If you haven't seen that, it's wonderful. It talks about Nash, who developed this concept of the Nash equilibria and basically transform the economics and everything. Okay. So yeah, let me check. Okay, so this is game theory, very basic. And if this works, okay, so the game that involved some robbery here, some robbers, will be the prisoner's dilemma. So let me remind you a bit of Yeah, as you can see, we've named a dilemma free. But anyway, yeah, for the prisoner's dilemma, we have two robbers there that are caught, and they are placed into two separate interrogation rooms so that they cannot communicate during the interrogation process. Then the police officer goes there and tells them, hey, if you both confess to the crime that we believe you have committed, then you both get 1 year in prison. If you both defect or deny the facts, you both get 5 years in prison. And if one of you confesses and the other defects, the one who confessed gets full sentence, gets 10 years, and the other is set free, gets 0 years. Okay? So this is the basic scenario of the prisoner's dilemma. And when you analyze this, the Nash equilibrium, which is a configuration in which no player wants to unilaterally deviate, is when they both defect or deny the facts. So they both get 5 years. Why? Why is this the solution? Well, you can see that there is another solution in which if they both confess, they both get 1 year. So it's a win-win, 1 year, and we're off. So when they are like together, they can say, let's confess. If we get caught, let's confess, because it would be better for both of them, for both of us. But then when I'm in the interrogation room and the other robber is in the interrogation room, because I know that he or she are going to confess, I will deny the facts, because it's better for me. If I confess, I get 1 year. But if the other robber confesses and I deny the facts, he will get or she will get 10 years and I will get 0 years. So in a sense, this solution of both confessing is not rational, because I could get better off if I just defect. Okay. So the Nash equilibrium there is when they both defect and they both get 5 years in prison. So what is the name of the dilemma here? Well, it's because, as I said, there's another solution, which is when they both confess, which would be the best for both of them. But it's not a rational solution. The rational solution is when they both defect. So there's the dilemma. Rationality tells me that I should defect, that both of them should defect. But there is another solution which would be better for both of us. So what should I do? But in the classical scenario, the solution is when they both get 5 years and they both defect. What about the quantum version of that? Well, the quantum version of that was proposed by these people, Iser, Wilkins, and Levenstein, in this paper in '99. Okay. And their approach is slightly different to what I'm going to present, but the idea is the same. So in the quantum prisoner's dilemma, we have the two robbers, but when they are together, they decide to share a quantum state with two qubits, qubit A and qubit B. Qubit means that there are two possible outcomes when I measure, either 0 or 1. Okay? And they have two qubits. And in quantum mechanics, the fact that you can have two qubits doesn't always mean that the description of that is done separately. Okay? Even though I have two things, the description can be done as a whole. Okay? That's what is represented here. We describe this state as one thing. Okay, quantum mechanics is great, but it doesn't prevent them from getting caught. So they are placed again in their interrogation rooms, but this time they have their qubit. Think of the qubit as a photon, for instance. So this guy has qubit A and this guy has qubit B. But again, no matter how far apart they are, the description of this state is done as a whole, even though there are two separate parts. Okay. So they are in the interrogation room, and what happens is that they will perform a quantum operation on their own qubits. So, oops, this guy will do a quantum operation on his own qubit. So it will be changed to another state. And the same for the second guy. So if they started with an initial state, after they perform a quantum operation, they will end up with a final state. And then after the final state, they will measure. They will measure their own qubit. And as I said, qubit A can be either in state 0 or in state 1. If they find that the state is 0, they would both confess. If this robber finds his qubit in state 0, they will confess, and if it's in state 1, they will defect, and the same for the others. So in a sense, this qubit is telling them what to do, if they should cooperate or defect. So let's focus a bit on what's happening. That was the full picture. Let's focus a bit on this, the initial state, and on this quantum operation. What is that? Well, for the initial state, if you're familiar with quantum mechanics, one possible example of an initial state would be described by this: 1 over square root of 2 over state 0 for qubit A, state 0 for qubit B, plus state 1 for qubit A as well, and state 1 for qubit B. So this state is a superposition of two states, of state 0, 0 and state 0, 1. 1, 1, sorry. This is another example of a quantum state. That it's done as a whole. Then quantum mechanics only allows certain kinds of operations on their qubits, and these are called unitary operations, which we denote by this U of A, which is the operation done by robber A, which is unitary, and the same for the second robber. Okay. So we have those two operations, and then they end up with a different final state. If they started here after a quantum operation, they will end up with another final state. Okay, so let's go back. Full picture: after they have their final state, they will both measure it and find if your qubit is in state 0, then you confess. If it's in state 1, you defect, and the same for the second robber. So again, this is the same picture. The strategy, or the strategy in the game theoretical framework, is encoded in the chosen operation of this unitary operation, which we will look into that in a couple of slides. And the measurement is what is telling them if they should confess or defect. Measurement of their own qubit. Okay. So yeah, quantum mechanics is all about probabilities of something happening. So we need to speak about the average times, average years in prison. So for instance, these are the conditions of the original game, both confess in 1 year, both defect in 5 years, and so on. So in this case, since we are talking about probabilities, the average years of robber A would be -1. We are counting years in prison, so it's a negative thing. So it would be the probability of both of them confessing times 1 year minus, plus the probability of both of them defecting. So robber A gets 5 years negative. Then the probability of robber A defecting and robber B confessing, that means that A gets 0 years. And finally, the probability of the other way around, which is when robber A gets 10 years. Okay? And as we said from this picture, the probability of them confessing corresponds to the quantum probability. The probability of both of them confessing corresponds to the probability of them measuring state 0, 0. Robert A measures 0 and Robert B measures also 0. Okay, so these probabilities are mapped into quantum probabilities. Okay, I think my computer is not that old. Okay, yeah. So yes, I was saying the average years in prison is just a probabilistic process now of something happening in the quantum setup. Okay, so that's great. Now let's look at what does that mean, this strategy choice of the unitary operations. Okay? But before we go into that, I need to take a quick break and I'm going to tell a joke. That's what I do. So the joke goes as follows. Where does an atom go when it breaks down? So quantum mechanics. I mean, it's good. I like it. Maybe it's not that good, but yeah. So does anyone have any questions so far from what I just explained? For the people online, you can put your questions in the chat. Has anyone in the room have a question so far? No? I guess no one then in the chat either, in the online. Yes, please. Can you repeat that? Yeah. When you have your yes. Yeah, kind of. In the classical version, you either choose confess or defect. So those are your possible strategies. Yeah. In the quantum version, since your probability of confessing or defecting is affected by what you have done in the quantum operation, yeah, your strategy is the quantum operation that you pick. I don't know if that makes sense. Yeah. Okay. Thank you. Thanks for the question. Then we can move on because we are going to look now at these unitary operations here. What does that mean? This is the basic setup is that. Now let's look at what happens with this. Well, okay. Okay. So the unitary operations. When the players, the robbers, choose their strategies between these two quantum operations, the identity, which is I won't do anything to my qubit, or I would apply this operation d hat. Okay, is different from defecting. The hat is the operation. Okay, without the hat is the usual defecting. So when the players can choose between this C, the identity, or this D, you recover the classical result. So if you give them, okay, you have the quantum stuff and everything, but you can only do this, C, the identity, or you can do D. Then the result is the same as if you didn't have this quantum setup. Okay. But that's very boring because quantum mechanics allows for way more operations than only the identity and the other one. So in general, if you restrict your quantum operation to be this matrix in general with two parameters, phi and theta, which is a valid quantum operation because this is unitary. And specifically, these matrices are matrices in the group of SU2, special unitary group. That means unitaries with determinant equal to 1. Okay? So this operation is also a perfectly valid quantum operation that you can perform on a qubit. And in fact, the C and the D here are just this U, but just pick two specific angles. So those two are just a special case of this. Okay. So now the players can do their operations can be encoded into this matrix form. Okay. For a maximally entangled game, if you don't understand what that means, is related to how they define the game. But it means that the quantum state that you have is maximally entangled. I can explain to you that if you have some questions at the end. But for a certain choice of a game, of an entangled game, both choosing this D, remember that this D is the classical one, corresponds to the classical result, is no longer a Nash equilibrium. This is the classical prisoner's dilemma. Remember that this solution was the Nash equilibrium. The quantum version, then, under these assumptions, that is not longer a solution, a valid solution of a Nash equilibrium in which no player wants to unilaterally deviate from it. Instead, we have a new Nash equilibrium, and this Nash equilibrium is achieved when they both perform this operation called Q. Okay, this Q is just a special case of this, picking the correct angles there. So the new Nash equilibrium is when they both apply this Q to their qubits, their own qubits. And when you do that, the expected payoff meaning the average time that they spend in prison, remember that it looks like this for A, and these are the probabilities, the quantum for probabilities and the confessing and defecting probabilities here. So when they apply this operation, they get the same result as if they were both confessing in the original game. Okay. So with that, this leads to the best solution, the Nash equilibrium. The solution for that is as if they were playing both confessing, which is the best solution. So in a sense, the dilemma disappears because now the solution is the best, is the one that is best for both of us. So it's great. So wonderful news, quantum solves everything. Well, that's not true because this model has some problems. In the picture that I just show you, this matrix, which is the special unitary matrices, 2x2 matrices, you are restricting the strategies that the players can do. In fact, in quantum mechanics, I said that the allowed quantum operations are unitary. So the group of matrices that you should be looking at is bigger than only this. You're restricting here your view to a special set of matrices. What happens is that when you allow any quantum operation that is unitary, including that, there is no Nash equilibrium, as we defined before, as the player one deviate. With pure strategies means that I will choose this. Mixed strategies, on the other hand, is I will choose this strategy with certain probability, then the other with certain probability. Pure strategies means I will choose that with probability 1 if you want. So yeah, when you allow for a more general scenario and more general and more correct, if you want, strategy space, then this doesn't work. There's no Nash equilibrium with pure strategy. With mixed strategies, which I just said is just a probabilistic mixture of strategies, you can find an infinite number of Nash equilibrium when you allow for all the possible quantum operations that you can do. And the payoff or the average time in prison is better or worse. You can adjust it by just changing these numbers. Okay. It's 1, 5, 10, and 0. Again, from the game theoretical perspective, this setup presents some problem because it's like the quantum state is acting like an advice in a sense. So which it differs from the original game in which they cannot communicate and they should just stick to their own reasoning, if you want. So in this sense, this quantum state could act like an advice, so it's kind of a different game. And other models of this also present these problems or similar ones. But it doesn't matter, because thanks to this proposal, this paper in '99, the field of quantum games started. There was no such thing before. And this field, it overlaps with other maybe more known or more famous fields, which are quantum computing, overlaps, quantum information, and quantum foundations of the quantum theory. So yeah, quantum games is kind of in the middle between all of them. So lastly, what I would like you to think or to know, to extract from today's presentation, is that a quantum game is any game that you can think of when we add quantum things, quantum resources somehow. As you said, as you just saw today, if we allow the players in the prisoner's dilemma to have a quantum state, you have a game and then you add quantum stuff. So that's a quantum game. And this is not only for fun, it has, as I said, several applications in quantum cryptography, quantum computing, and quantum foundations. So that would be it. Yeah, this is kind of the quantum computer that is from IBM, I think, the current one. So that's how a quantum computer looks like today. Hopefully it will, I don't know if we will be able to see a quantum computer at home. I don't know. But yeah, that's how the computer looks like now. So that's it from me. I will happily take any questions you might have. But again, I need to tell another joke. You already know it, Peter? But yeah, I asked a quantum physicist what her opinion on quantum superposition was. And she said, well, I'm neither here or there. Okay. Which one was better? This one or the first one? They're both really good. I know. I spend more time trying to find good jokes than actually doing things. So yeah, does anyone have any question or related to anything? I will sit down. Any questions or comments or? Yeah. So yeah, now if someone asks you at the door, what is a quantum game? Would you be able to more or less answer? Okay. Great, that's great. That's yeah. Well, just remember this. Any game with we add quantum stuff. That's a quantum game if you want. Okay, no questions. So yeah, thanks for coming. It's lovely to see people, and especially from NYG as well. So yeah, if you want to join QIreland or stay tuned, you can just go to the webpage here, or drop an email or anything. Yeah, is that okay? Okay. Then yeah, thanks for coming and have a happy Easter then. Yeah, no problem. Yeah. Well, only for the jokes.